S stands for symmetry. Is it an odd or an even function? Have a look at it, right? Again, in case you can't remember, if you think of this thing as f of x, right, f of x, then you're going to input negative x everywhere and then see what patterns you observe. So for instance, when I put this in, when you cube it, it'll be this, and you'll get that, okay? Now, is this either exactly the same as this, or is it this with a minus sign out the front? And the answer is no, it is neither of them. It's quite obviously not the same, right? It's quite obviously not the same. You'll only really get the same thing when all of your powers are even, hence even symmetry. In the same way, it's not an odd function either. What result would I need to get here in order for this to be an odd function? What difference? I'd need a minus 1, wouldn't I? Once you got that there, okay. Now, this actually is going to produce for me an even function, is it not? Like, because all of these negatives are going to cancel. Okay, so you get even symmetry. If I wanted it to be an odd function, I'd need, what would I need? What would I need?
Get rid of the minus.
Which minus should I get rid of? Probably the bottom one, because then that's just one of them. Okay, so now you can see that's the effect of putting a minus sign out the front and brackets. So there you go, that would give me an odd function. I don't have either of those, so unfortunately I don't get to take advantage of this symmetry. But it was a pretty quick thing to work out. That. Okay, so it's out of the way. Next step, factorize. Okay, now admittedly, we haven't looked at this for a while. I'm going to get rid of this since it's not useful to us. So we don't do much work with cubics, but that numerator there, it can be factorized. How do you factorize it? It's going to be, all right now, if you can't remember the sum and difference of cubes, okay, the sum and difference of cubes, this is the way the sum and difference of cubes works, okay? The first thing that I do is I remember what are the pieces that go into it, and then I do the signs afterwards, right? So I know that it starts with this, and it goes through like this. These are the pieces, okay? One of the ways I remember this is that this bit in the middle here, it can't be a 2, because if it were a 2, I'd be able to factorize further, right? I'd be able to make it, well, this would be a perfect square of some description, okay? But it can't be. Like, the whole point is that this is as factorized as it can go, okay? Now, the last step after you get all the pieces down is to remember the signs, and we use SOAP, right? Okay, so I'm starting with a plus, so my signs will be same, opposite, always positive. Nailed it, okay? So therefore, in this context, where all I've got is x³ plus 1, right? Think about what your a and b are going to be. You should get this. Sorry. Opposite, always positive. Done. I've factorized it. It's not particularly beautiful, okay? But it's enough. It's all I need. Okay. So, from here, I'm going to look for, I've factorized it, so what am I going to look for? What feature am I going to look for next? Asymptotes. Very good. So let's draw ourselves a set of axes and start to put this thing on here. There are hard asymptotes and there are easy asymptotes. Which one's easy to spot? The vertical one. You go straight to the denominator, you'll let it equal to 0, x equals 0, that's my vertical asymptote. Yes?
What happens if you, there's no asymptote you can get from there?
If there is no vertical asymptote, yeah, I'll look at that next, actually, if that's okay. So in some cases, the denominator can never equal 0, so that means no vertical asymptote. You're going to have to look for the descriptive features of this graph elsewhere. Right, so we got x equals 0. That's a plus. Now we get to the harder part, and this is why this is the part that I'm interested in this particular question. Okay, we're either expecting an oblique or a horizontal asymptote. Okay, now immediately we can rule out a horizontal asymptote. There's no horizontal asymptote here, and the reason why is we look for the degree. Okay, the degree of the top is 3. And the degree of the bottom is 1, so the degree of the top is bigger, right? In order for a horizontal asymptote to emerge, what would we have if we wanted that?
X squared, x squared.
Yeah, they've either got to be the same, right? Or the bottom should be bigger, right? Make sense? And we don't have that. So we're expecting an oblique asymptote. But then the problem here is because I don't think I've given you other questions like this. Yeah, I don't think so. Is that the degrees, they don't differ by just one. Right? If you had like x squared something 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 divided by x, just thinking about it in polynomial terms, right? If you divide degree 2 by degree 1, you would expect that what you get is degree 1, right? Like it's like an x squared divided by an x, you get an x, right? In the same way, if I bumped it up and went degree 3 divided by degree 2, again, you'd expect degree 1, right? Because like x cubed over x squared will still be x, okay? But here I have a difference of 2, degree 3, degree 1, right? So therefore, when I divide, I ought to expect, not degree 1, but the difference will be 2, right? It's just ordinary division. It's just index laws, right? Now, you can bear this out by seeing, do you remember we looked and we saw to find the actual equation of the oblique asymptote, right? To find if it's like y equals x, or x minus 3, or whatever, we had two ways. One was the cheap way, which sometimes works and it's fast, and there was a more sophisticated way. Do you remember what they were? What were the two ways? Method 1, right? It's when you get something like this. If I give you this, okay? This is very easy to just break apart into two fractions, right? When the denominator is a mess, you can't break apart denominators, but numerators, you can, right? This guy would just be x minus 1 on x. Okay, I've broken it apart. I know that this part will go towards 0, so there. That is my oblique asymptote, okay? Method number 2 is if you get something a little bit messier. So if I have, say, this, there we go. Okay, I can't very neatly or straightforwardly break that apart. So what do I do in this case? I have to resort to polynomial division, long division. It's not a fun process. It's long, right? Long division, but it can be done, and then you get an answer at the end. Have a look. Which method would you resort to in this case? You can do method 1. You're just dividing by x. This is pretty easy, right? So when you divide it, one of them will be x cubed on x, which is x squared. And then the other part will be 1 on x. Okay, so then you look and you're like, all right, I've already isolated that part that is going to be approaching 0. Okay, so all I'll be left with therefore is x squared. X squared. Okay, what does x squared look like? Well, that's what x squared looks like, right? Be weird, but that's what the algebra tells me. That's what I should be approaching, okay? Now, I could go a little bit further. Let's just think about, we've done asymptotes now. I'm done, okay? My next feature that I'm after are intercepts, right? You can see right away there's no y-intercept, right? There's no y-intercept because I've already identified this asymptote, so I don't have to worry about that. There is an x-intercept though. How do I find the x-intercept?
You look at the top.
I look at the numerator, right? And this is the whole point of factorizing, okay? Right there, I can see therefore my x-intercept is going to be -1. So I'll chuck that guy over here. Okay. You can go ahead and you can try to solve this quadratic over here, but it has no solutions, which means there are no other intercepts. Okay. Last little piece, regions. Okay. How are we going to do the regions on this? We're going to do it in. I'm going to do it in a kind of quicker way, right? So you can see, right? You can see I've got what's happening over here. X plus 1 is one of my factors. Okay, so I'm going to put that in green. There's x plus 1. X is another of my factors. It looks like this. Okay. And then we have one last factor, this awkward quadratic guy. Now, a question I received was, what happens when you can't factorize that anymore? Like x squared minus x plus 1, that's as far as it goes, okay? And the answer is, think about it. Why are we drawing these factor lines? The reason the factor lines are useful is because we know when they're positive, we know when they're negative, and so we can combine them to work out the whole thing. Okay. Now, I've accounted for this. We just determined, by going through this process of trying to find intercepts, we just determined that this will give us no intercepts. This thing never equals 0, correct? Okay. But at the same time, it's a parabola, right? And it's a parabola that's facing upwards. It's concave up. I can tell that because it's an x squared, not a minus x squared. That would be facing downwards. That would be sad, right? So being that it never touches the axis and it's concave up, right? I'm not even going to draw this factor in because it's always positive. Does that make sense? This guy, whatever value of x you throw in there will always be positive, so it's never going to change the sign of this whole result, okay? It's a little bit like if I said to you, okay, a positive and a negative, okay? We know if you multiply or divide these, you're going to get a negative, right? Now if I just add another positive number in the mix, and I tell you, it always has to be positive, okay? What effect did that have on the sign? Answer, no, it doesn't change it, okay? So therefore, it doesn't affect my regions, so I'm not even going to draw it. If I were to draw it, it would be a parabola up here. And that's just clouding my diagram, doesn't contribute anything, so I'll just leave it off, okay? So therefore, I'm now going to look and I can see, all right, I've got two negatives here, right? Two negatives here, so therefore I'm going to be positive, right? All right, so roughly speaking, so my graph doesn't turn into a mess, I hope you can see. I'm basically doing, positive, negative, positive. Can you see it? Can you picture it? I'm not going to draw it on. I'm not going to color it. Okay. I think I have enough information. I think I have enough. Let's just think about to the left of this asymptote over here. I have to go from positive to negative, and I have these two asymptotes that I need to approach. Okay? So therefore, it looks to me like I'm going to do this kind of thing. What else can it do? Right? Like I have to get closer to this asymptote up here, so that's why I'm hugging in. I have to cross this intercept, and then I have to start getting towards x equals 0, but never get there, right? So that's all I can see. Now, just a little note, like you know how we talked about when you can cross oblique, or I wouldn't know, like you wouldn't call that an oblique asymptote because it's not a straight line. You call it a parabolic asymptote, I guess. Okay. How do I know I don't cross that? Okay. The way I would think about it is come back to this guy. This is how we got the parabolic asymptote in the first place, right? So when you do this, I'm thinking about this is negative side, so negative infinity, okay? You're approaching x squared. When you're negative, we're used to thinking of this as it's approaching 0, right? It is approaching 0. But which way? Which way is it coming from?
From the top.
Now, if x is negative, very, very, very negative, right? Then this whole thing is a very, very tiny negative number. Does that make sense? Like minus 1 over 1,000 or minus 1 over 1,000,000, etc. So I'm actually coming from the bottom, right? It's x squared and you take away a little bit. When you take away, it means you're underneath, okay? So this is one of the ways that I can see I must approach this asymptote from the bottom, or it kind of looks from this perspective from the outside, okay? So that's how I know I don't cross over. It's just another way of determining it. And there's my intercept. Okay, so I've done the left-hand side, bless you. Now I'm going to do the right-hand side. Again, I know I'm positive here and I'm locked in between these two asymptotes. So what would you guess that it does? It just kind of, it kind of looks like a parabola. It's actually nothing like one, but I mean, in terms of the numbers. But that's what you've got. That's what you've got. I've got a point for scale on this left-hand side because an intercept is there. I don't have a point for scale on the right-hand side. So would you like to give me a nice easy number? Yeah. 1. How about 1? 1 cubed plus 1 is 2, and then you divide by 1. So it's going to be like 1, 2. Okay? I don't know, by the way, if that's right on the bottom. Actually, I don't know exactly where it is, but I have it approximately, and that's, for now, all we need to know. Okay?